Let's talk about dirt, specifically the wet, unstable kind that makes building stuff a real pain. That's where prefabricated vertical drains, or PVDs, come in. Think of them like giant wicks stuck in the ground. They're not glamorous, but they're essential for building on soft soil. Roads, bridges, airports. If it's built on muck, chances are PVDs were involved. They're the unsung heroes of construction, making sure things don't sink into oblivion. These drains aren't just stuck in the ground randomly. There's a science to it, geotechnical engineering. It's about understanding the dirt, how it behaves under pressure, and how to make it stable enough to build on. And that's where PVDs really shine. They give that soggy soil a way to drain, letting the water out and the ground settle faster. It's like squeezing out a sponge, but on a much larger, more technical scale. Now let's get our hands dirty, literally. PVDs are pretty simple in design, which is part of their beauty. Imagine a plastic straw, but flat and with tiny channels running down its length. That's the core of a PVD. It's usually made of polypropylene, a tough plastic that can handle being buried and squeezed for years. Surrounding that core is a filter fabric, like a sock. This fabric is crucial. It keeps the soil out of those tiny drainage channels, preventing clogs. It's like a coffee filter, only instead of coffee grounds, we're keeping muck from gumming up the works. Without that filter, the whole system would be useless. The science behind PVDs is all about consolidation. When you put weight on wet soil, the water gets squeezed out and the soil compresses. But that takes time, sometimes decades. PVDs speed up that process dramatically. They act like shortcuts for the water, giving it an easy escape route. This means faster construction and a more stable foundation. Don't let the simplicity fool you. Building these drains is serious business. We're talking high-tech manufacturing to make sure every PVD is tough, efficient, and built to last. It starts with the core, that plastic straw. It needs to be strong enough to withstand the pressure of tons of earth, but flexible enough to bend without breaking during installation. Then there's the filter fabric. This is where things get really technical. The fabric needs to be permeable enough to let water through, but fine enough to keep even the smallest soil particles out. It's a delicate balance, and manufacturers use sophisticated materials and weaving techniques to get it right. But it's not just about the materials. The dimensions of the PVD, the size and spacing of those drainage channels, the type of filter fabric, all of these factors are carefully calculated by engineers. They consider the type of soil, the weight of the structure, and even the local climate to create the perfect PVD for the job. Installing PVDs is where the rubber meets the road, or more accurately, where the plastic meets the mud. It's a carefully choreographed dance of heavy machinery and precise movements. First, a specialized rig, basically a giant hydraulic hammer, drives a steel casing into the ground. This casing acts as a guide for the PVD. Next, the PVD itself, pre-attached to a steel mandrel, is inserted into the casing. The mandrel is like a long, thin sword that protects the PVD during installation. Once the PVD is at the desired depth, the mandrel is retracted, leaving the drain in place. The casing is then pulled out and the process repeats. The whole operation requires a skilled operator who knows how to handle the equipment and understand the soil conditions. They're constantly adjusting the pressure and angle of the rig to ensure the PVDs are installed correctly. It's a dirty, demanding job, but somebody's got to do it. Section 5, improving geotechnical performance with PVDs. So we've got these plastic straws in the ground. How exactly do they turn muck into a solid foundation? It's all about speeding up consolidation. Remember, that's the process of water squeezing out of the soil, allowing it to compress and become denser. PVDs act like express lanes for that water, shortening its journey and accelerating the whole process. Without PVDs, that water would have to slowly seep through the soil, taking years, even decades, for the ground to fully settle. With PVDs, that time can be reduced dramatically, sometimes by as much as 80%. That's a huge time saver, especially in large-scale construction projects where every day counts. But it's not just about speed. PVDs also improve the soil's strength and stability. By removing the water, they increase the soil's bearing capacity, meaning it can handle heavier loads without sinking. This is crucial for supporting structures like buildings, roads, and bridges. Section 6, applications in infrastructure and beyond. PVDs are like the duct tape of geotechnical engineering. They're incredibly versatile and have a wide range of applications. You'll find them in just about every type of infrastructure project built on soft soil. Roads, highways, railways, they all rely on PVDs to provide a stable foundation. Airports are another prime example. Runways need to be incredibly flat and stable to handle the weight of landing aircraft. PVDs are essential for building these runways on soft ground, ensuring the safety of passengers and crew. But it's not just about traditional infrastructure. PVDs are also used in land reclamation projects, turning swamps and marshes into usable land. They're used in environmental remediation, helping to contain and treat contaminated soil. They're even used in offshore wind farms, providing stability for the massive turbines. Section 7. Design parameters and quality assurance. Designing and installing PVDs is a science, not a guessing game. Geotechnical engineers use sophisticated software and calculations to determine the optimal spacing, depth and type of PVDs for each project. They consider factors like soil properties, expected loads and even the local climate. Once the design is finalized, it's all about quality control. Engineers monitor the installation process closely to ensure the PVDs are installed according to specifications. They use instruments to measure the depth and alignment of each drain, making sure everything is up to snuff. They also conduct tests to verify the effectiveness of the PVDs. This might involve measuring the rate of consolidation, monitoring pore water pressure, or conducting load tests. It's all about ensuring those PVDs are doing their job, keeping the ground stable and the project on track. Section 8. Numerical modeling and analytical techniques. Remember that sophisticated software I mentioned? It's not just fancy graphics. Geotechnical engineers use numerical modeling techniques to simulate the behavior of soil with and without PVDs. These models help them optimize the design and predict how the ground will behave under different loading conditions. One common technique is finite element analysis, which breaks down the soil into tiny elements and calculates the stresses and strains on each element. This allows engineers to identify potential weak spots and adjust the design accordingly. These modeling techniques are constantly evolving, becoming more sophisticated and accurate all the time. This allows engineers to tackle more complex projects and push the boundaries of what's possible with PVDs. Section 9. Regulatory standards, emerging technologies and benefits. Like everything in construction, PVDs are subject to regulations and standards. These standards ensure the quality of the materials, the safety of the installation process, and the effectiveness of the final product. They provide a framework for engineers and contractors to follow, ensuring consistency and reliability. But the field is constantly evolving. New materials, installation techniques, and monitoring systems are being developed all the time. For example, some companies are experimenting with biodegradable PVDs made from natural fibers, reducing the environmental impact. And the economic and environmental benefits of PVDs are undeniable. They reduce construction time and costs, minimize excavation and waste, and improve the sustainability of infrastructure projects. So next time you see a construction site, take a moment to appreciate the humble PVD. It might not be glamorous, but it's playing a vital role in shaping our world.